Hello, my name is Paulos. I'm a senior scientist and principal investigator at Raytheon BBN Technologies. I'm presenting priority-enabled load balancing for dispersed computing. This is joint work with the University of Iowa and the University of Tennessee in Knoxville. This talk is divided into 4 sections. In the first, I'll motivate the need for priority-aware service placement of critical fog and edge applications. In the next 2 sections, I'll describe recent research results from the DARPA Dispersed Computing Program, where our team is maturing an agent-based middleware for managing the placement of computational tasks and data into widely distributed compute networks. I'll follow with a summary and future research directions. As a natural evolution, economy of scale and ease of use led to a massive movement to consolidate most services and data into the cloud. This migration included functionality and data that are critical to tactical edge users such as emergency responders. Consider a disaster recovery scenario where population data, registry of properties, medical data, and coordination support services like chat and screen sharing are centralized and require backhaul internet access. In such scenarios, network connectivity is not guaranteed, and at best, networks would be highly congested and intermittent. A typical solution has been to install mobile cell towers or satellite links to reestablish backhaul connectivity. While this reestablishes connectivity, there may still be range, capacity, and cost issues. With the advent of fog and edge computing, the centralized backhaul model is changing in at least 2 ways. First, compute and store resources are evolving at the edge and within the network itself. Different collections of edge hardware may be used to adaptively host data and services to meet emerging demands of different criticality and importance. Second, the computing infrastructure may retain some level of network connectivity due to the emergence of new and accessible radio technologies such as 5G. This slide illustrates a representative sample of dispersed computing environments. Building on fog and edge infrastructures, communities are envisioning and realizing improvements to a broad range of locavore applications. In the tactical defense domain, examples include improving the quality of service for various situational awareness and understanding applications, possibly in dynamic federated scenarios. Another example might be enabling fast runtime provisioning of results from digital world-building applications, especially in data-hungry deployments like processing multiple sensor feeds from drone swarms. Tactical defense users face unique challenges. They often operate in remote environments and may not have robust, always-on connectivity to the cloud. Furthermore, they operate in contested environments that necessitate adaptive resource management to schedule access to ranges of equipment and applications at different times. As such, the range of needs cannot be met with only pre-positioned and provisioned edge resources. In terms of related work, when we look for mission awareness or priority placement in fog and edge environments, we only found a single reference out of 400 surveyed research papers. It happens to be within the emergency response domain, which makes a lot of sense. On the other hand, the actual management software middleware that's being deployed onto compute environments is highly compartmentalized by concerns. For example, K8 does an excellent job managing local clusters that are co-located and co-schedulable. At the same time, it delegates a lot of concerns to third-party tools like management of on-cluster and external load balancers, where these complementary components are essential for dispatching clients into disjoint clusters globally and responding to dynamic events. The implication here is that global priority-enabled allocation and dispatching would need to be threaded through a number of layers, not just within a single scheduling domain. This has the potential to end up with very brittle solutions that don't enforce priority well. We see several key resource management requirements for mission-oriented scenarios. First, any type of placement software or allocation software needs to enable the optimized placement of data and services, get it closer to the people that actually need it. As a broad objective, they should also attempt to minimize backhaul traffic and latency in disaster scenarios. And furthermore, the task placement capabilities not only need to be accurate, they have to be robust and resilient to failures in face of emergent events. And these can be catastrophic events like a cluster going down in a fire, or something like a hotspot where a lot of flare-up and need for computation is occurring. And furthermore, this should include all primitives for coordination, the algorithmic designs, and the infrastructure that's used to migrate data and monitor resources as they're actually running. And so the key focus of our talk is really on adding prioritized resource allocation and dispatching capabilities across compute clusters as first-order citizens into these middlewares. And this should help prioritize on a need basis, access to resources. All right, we'll move on to the next section of the talk. To design priority support, we build on top of the MAP middleware. MAP stands for Mission-Oriented Adaptive Placement of Task and Data. It's designed as a distributed multi-layer framework for decision-making and resource management in dispersed computing networks, the types shown on slide 3 of this talk. MAP has already shown promise in distributing computational services in a scalable and resilient way, mostly to minimize backhaul traffic and improve client performance. We've also evaluated in failure scenarios, where there's changes in demand, extreme hotspots and stress test scenarios, and failures of networking links and compute resources. The architecture slide's a little busy, and so I'll walk through this and describe the areas that we're focusing on in this talk. On the left-hand side, we show the network organization of MAP, and so this is really the highest layer of the system, where we break down computational resources across the global network into smaller groups of regional computational resources. A region can be thought of as a tightly connected area with different computational resources, and in between regions there could exist either strong or weak links. To manage spillover of client demand or excess load within a region, we implement a distributed constraint optimization problem that reasons about network links and loads and sources and destinations of demand across the network, and can kind of smear the computational boundary across the regions. Within each computational point, we place a map agent. MAP's an agent-based architecture that can manage or interface with a containerized or a virtualized environment. We've implemented bindings for Docker, and we have a hardware abstraction layer that can be bound to other things like Kubernetes. In the regional layer, the map agent runs a component called the Regional Load Balancing Gateway, which is responsible for a tactical allocation of tasks, spinning up containers, stopping them, and associating the clients with the services in the network, which we refer to as dispatching. And it's very appropriate. We're dispatching through a DNS mechanism that we've modified to support hierarchy across the regions. So for the remainder of this talk, I'll really be focusing on the DNS component and the RLG component, and how it performs both allocation of tasks in a prioritized way and associates clients with services using a couple of different strategies. All right, this is the meat of our presentation, is in the next few slides. This is about our extensions for prioritized allocation and dispatching. As I mentioned in the previous slide, we've implemented support for mission awareness in the Regional Load Balancing Gateway component of MAP. This manages the decision-making that controls spin operations and unspin operations, or bringing up new sets of services and tearing them down through that hardware abstraction layer. It's also responsible for putting the policies in place which associate clients within a network with tasks that are executing on clustered environments. So there's really two things we're taking a look at here in our initial analysis and some of the experimental evaluation. One is two different types of dispatching strategies, a round-robin strategy, and we compare and contrast that with a load proportional strategy, which looks at load on containers and tries to fit the client requests into containers based on how loaded they are. We also designed and implemented two priority allocation schemes, one inspired by just a strict greedy scheme, where the most important services by definition, and I'll tell you what that is in a second, are granted access to computational resources. And a second scheme, which is inspired by more fair queuing type approaches, which is a priority weighted reservation scheme. As a notion of importance, we define this as task importance to the operation at hand. And so in a recovery scenario, you may prefer situational awareness type tasks over lower priority background tasks like site surveys through drones that are doing digital world building. Alright, in the next 4 slides I'll take a look at an analysis of the DNS assignment rules, or the dispatching rules that associate clients with servers in the network. As I mentioned, we were looking at round robin without waits and proportional remaining to capacity. These are initial results where we basically modeled the two different operations of round robin proportional. The key observation here is that the proportional tends to equalize load across containers better than round robin will. And we have a couple of graphs that hopefully can convince you of that. So the first one is these two. I'm not going to go into these in a lot of detail, but the key idea here is that when you're using round robin and you're spinning up new services, you're really hitting the first container all the time. Every round you're coming back and hitting that first container. And so it's pushing more and more load in it, and as you start filling up a region or a set of containers, you're going to potentially overload that first container, and it'll lead to drops more. Whereas proportional in comparison, when it sees that first container overloaded and other jobs completing, it'll push things off. We also show that here in a slightly different graph, looking at two different containers. And it shows the same type of criteria, that proportional distribution drops jobs no earlier than round robin. So what concluded, it's always better to use proportional distribution versus a strict round robin type approach. So shifting gears, we take a look at the allocation strategies. We broke up the two algorithms that we implemented into lower level strategies that they build upon. Replacement policies, reserve, proportional reserve to priority over time, and temporal reserve patterns to priority and load over time. The last one is more in the prediction type category, where it assumes that there's good estimates of both arrival and retirement rates for jobs. And MAP can provide this information. The agents can collect it and disseminate it as needed. So we implemented two of these algorithms, but we actually analyzed an additional one, which was greedy with prediction. And the key observation here is that the temporal reserve strategies with accurate load estimates, so this is in the prediction category, and retirement can lead to less priority inversion and self-correction as new loads and priority mixes arrive. So basically what that's saying is if you have a good oracle or a good ability to measure how well the jobs are completing and how long it's taking them, when they're arriving, you can do a better job at assigning resources. And that information is not always available, especially in disaster type scenarios. So this table, I'm not going to go into this in detail, but I'll try to give you a quick flavor for it. There's really three tables here. There's a potential hypothetical workload on the left-hand side, where we look at service loads for a high, medium, and low priority service at one time step in the past, a time step current, and a time step in the future. And what we see when we look at this is that the proportional strategies can lead to a type of priority inversion when you're dealing with more than two services. And so in this case, there's basically more load, more demand for the lower priority service, and it's potentially starving out some of the medium priority service. You don't see that behavior in greedy, but you do see strict usage of resources based upon priority levels. And you don't see either of these properties with the greedy with prediction, which is on the right-hand side. All right, in the next few slides, we take a look at experimentation on the Emulab testbed using our greedy group implementation and reservation implementation. We use a 40-node computational graph with 4,000 P clients dangling off the edges. The clients are producing a 4x flood of demand over available capacity as shown in the demand graph on the right-hand side. The black dotted line shows computational capacity, and each of these higher priority services in turn is demanding more and more of those resources. So you might want to think about this in terms of first responders, where you can have low priority operations such as clients moving house to house, querying census data or uploading pictures, versus something that's much more important, like an EMT or a medevac type rescue that's occurring at a later date. So these traces show single runs of multiple iterations of these experiments. The top two runs, or the top two rows, show map, the greedy, and reservation implementations. The bottom row shows without map. On the left-hand side, we show allocation, which is spinning up containers, and the right-hand side shows actual load process, the demand being processed in response to the available resources. So we see a couple of clear trends here. First, the greedy allocation, each of the these subsequent pyramids is replacing it. So it means that the higher priority service is eating up resources. In a reservation scheme, as we go out the long tail of the graph between 8,000 and 12,000 seconds, we see that there's more fair allocation and a more fair usage of resources across the different priority groups. So in some preliminary results, we also took a look at load process versus the baseline, which is on the left, and total load process on the right, which is in log scale. We only looked at the priority waves, so the start of a new priority application until the end of the next application starts up, and looked at the amount of work actually done on the containers relative to the map baseline for the chart on the left, and relative to all the three different configurations in the chart on the right. So in general, we saw, across both the traces and these initial load plots, there's validation of the analytic predictions about the priority implementations. We also see significant gains over the baseline, which is shown in the chart on the right, up to 4.1x. And this is a function of the topology and demand scenario to some extent. We also see clear evidence that the greedy and reservation schemes can fit different use cases. So there may be scenarios where you only want to process the higher priority workloads that are available, and that's certainly where greedy is more important than a reservation type scheme. All right, in the next couple of slides I'll wrap up. So in summary, tactical users of edge and fog resources will require prioritized access to contested resources for a number of reasons. However, the state of practice resource management in Middleware that provides elasticity at the edge is not necessarily mission friendly. Unified mission awareness requires threading something like priority or importance through a number of components with separated concerns. In this work we did just that. We implemented 2 resource management schemes and 2 dispatching schemes within a natively dispersed computing middleware. In our analysis, we show clear gains from cross-node proportional load balancing over a naive round-robin approach. That is to say that the proportional load balancing is a preferred approach. We showed that reservation allocation schemes can lead to certain types of priority inversions under different workloads. And then we suggested that predictive job information, including rate of arrival and completion, will enhance the scheduler accuracy. We then prototyped these algorithms and showed empirical results that verified some of the analytic claims and further showed mission awareness in the implementation. The code's open source and available at this link. In terms of short-term research directions, there's 3 areas we're interested in investigating. This work primarily considers working with legacy applications using only trailing estimators of demand and load. A complementary approach would be to incorporate predictive load estimators. Another area to look at is very large scale scenarios, not necessarily just within a geographic area, but also where other attributes come into play, like jurisdiction, and this prompts a deeper use of the dispersed computing concepts within the map middleware. And the final area is applying mission awareness in mobile edge compute scenarios where there may be periodic or ephemeral computation and storage that's available from vehicles that are coming and going. All right, I'm happy to take any questions. Once again, I'm Aaron Paulos. My contact information is at the front of this presentation. All right, thanks. Hope you enjoyed.